we are going to discuss about the magnetic effects of electric current. In this segment, we are going to discuss about magnet and magnetic properties, magnetic field and properties of magnetic field lines. Magnetic effect of electric current has wide applications in magnetic trains, telephone, electric motors, doors of refrigerators, electric bells, loudspeakers, etc. Traditionally, the ancient Greeks were the discoverers of magnetite. There is a story about a shepherd in Magnesia named Magnus, whose shoe nail stuck to a rock which was nothing but lodestone or magnetite. The history of magnet begins with this first discovery of magnetic stones or lodestones. It is formed by natural way of volcanic activity. Magnets are classified as natural magnets and artificial magnets. Natural magnets are naturally occurring magnets in nature as lodestone or magnetite, which do not have definite shape, while artificial magnets are man-made magnets with definite shape named based on their shapes. The strength of natural magnets are weaker as compared to the artificial magnets. Artificial magnets are named based on their shapes as bar magnet, horseshoe magnet, needle magnet, cylindrical magnet, oval-shaped magnet, ring magnet. Now let's discuss the properties of a magnet. A magnet has two poles, north pole and south pole. The magnetic force is strongest at the poles. We observe here the iron filings are more attached at the poles rather than other part of the magnet. A freely suspended magnet always comes to rest in the north-south direction. A magnet always attracts the magnetic substances and objects made of iron and steel. The poles of the magnet always exist in pairs. They cannot be separated. That is, if a magnet is broken into pieces, even a small bit of a magnet has two poles, north pole and south pole. They cannot be isolated. Another important property of a magnet is like poles repel and unlike poles attract each other. That is, north pole and south pole repel each other, while north pole and south pole attract each other. A freely suspended magnet always comes to rest in the north-south direction because Earth itself behaves as a huge magnet. The south pole of the Earth's magnet points to the geographic north pole and the north pole to the geographic south pole. The magnetic poles do not coincide with the geographic poles. An English physician, natural philosopher and a physicist, William Gilbert, was the first to propose that a magnet aligns in north-south direction since Earth behaves as a magnet. He also first made artificial magnets by rubbing iron with lodestone. Another leading scientist of the 19th century, Hans Christian Oersted, a Danish physicist and a chemist, first observed that a compass needle deflects when placed near a wire carrying a current. He gave the first evidence of the connection between electric and magnetic phenomena, which created technologies such as radio, television, and fiber optics. In honor of his contribution, the unit of magnetic field strength is named after him as Oersted. Let's conduct a small activity to know the relation between electricity and magnetism. A straight thick copper wire is placed between the points X and Y in an electric circuit, and a small compass is placed near the copper wire. By closing the electric circuit, current is passed to the copper wire. We observe the needle in the magnetic compass deflects. It means that the electric current through the copper wire has produced a magnetic effect. Thus, electricity and magnetism are linked to each other like the two faces of a same coin. Let's visualize a magnetic force exerted by the magnet. Sprinkle some iron filings around a bar magnet placed at the center of the board and gently tap it. The iron filings align themselves in a particular pattern, forming curved paths. This demonstrates the magnetic lines of force. A magnetic compass, in fact, has a pivoted needle magnet approximately pointing towards north-south direction. When a bar magnet is brought near it, due to the influence of the magnetic force, that is, like poles of a magnet repel and unlike poles attract each other, the compass needle gets deflected. Thus, we can define a magnetic field as a region around a magnet where the magnetic force can be felt. Magnetic field lines could be drawn by placing a magnetic compass near a bar magnet. Let's know to draw the magnetic field lines. Place a magnet on a sheet of white paper and mark the boundary of the magnet. Place the compass near the north pole of the magnet. We observe the south pole of the needle points towards the north pole of the magnet and the north pole of the compass is directed away from the north pole of the magnet. Mark the positions of the two ends of the needle. Now move the needle to the new position such that its south pole occupies the position previously occupied by its north pole. In this way, marking the points proceeding step by step till we reach the south pole of the magnet. Join the points marked on the paper by a smooth curve. This curve represents the magnetic field line. We can repeat the same procedure and draw as many lines as possible. These lines represent the magnetic field around the magnet known as the magnetic field lines. Magnetic field is a quantity that has both direction and magnitude. The direction of the magnetic field is taken to be the direction in which a north pole of the compass needle moves inside it. Therefore, by convention, the field lines emerge from north pole and merge at the south pole. Inside the magnet, the direction of the field lines is from its south pole to its north pole. Thus, the field lines are closed curves. The strength of the magnet is shown by the degree of closeness of the field lines. That is, more the strength of the magnet, more would be the closeness of the field lines. The field lines are close together near poles and spread out away from them. That is, the strength of the magnet is more at the poles. And also we observe no two field lines cross each other. If at all, if the two field lines cross each other, it would mean that at the points of intersection, the compass needle would point towards two directions, which is not possible. The relative strength of the magnetic field is shown by the degree of closeness of the field lines. That is, more the strength of the magnet, more would be the magnetic field lines, and vice versa. The magnetic field lines around a horseshoe magnet are observed in this manner. Thank you.